Talk about colligative properties. So colligative properties are, I guess it's kind of like what happens. It sort of tells you what happens when you take a solvent or something and you add and dissolve a solute in it. What's like kind of the macroscopic thing that you observe. How does the boiling point change? How does the vapor pressure change? Those types of things. Before we get into that, let's take a look at some things that will be useful when we get in here. So that the colligative properties are dependent on concentration of whatever you dissolve in solution. And so it's useful to kind of go over what are some generally closely related but not exactly the same things in chemistry. Remember, molarity is like the most common unit of measurement that we use in chemistry. And it's just the moles of a substance that we have dissolved in 1 liter. So it's a concentration that is units of moles per volume. Molality, which is really all, I think this is maybe the only section that we use it in. Molality is not units of mole per volume, it's moles per mass of a solvent. So kilogram of a solvent. So up here we're talking about 1 liter being an actual volume that, like that's 1 liter mark. Here, when we're talking about a kilogram solvent, it's like, well, I take out a scale and, I want to weigh out. I start adding in whatever my solvent is until I hit the 1 kilogram mark, so 1,000 grams or whatever. In the end, they're just measurements of how much solute you have per unit of solvent that you have there. But if you mess it up, it will mess up your, your calculation and your answer. And molality is much more useful. Molality is much more useful, I guess, for when you're dealing with these colligative properties for whatever reason. And then the last thing is just mole fraction. And mole fraction, I don't know that this is really a unit per se. It's more just, we use it a lot in the pressure laws, the partial pressures and stuff. That's why I bring it up here. But it's just to say that the mole fraction of a particular substance is the number of moles of that substance. So let's say you have a substance that has A and B and C in it. So I've got A, B, and C dissolved in some, let's say solution, or it's in the gas. More often or not, it's in the gas. So you've got 3 different gases. The mole fraction will be the number of moles of A, so the mole fraction of A, divided by the total number of moles in T, where the total number of moles is really just the sum of the individual numbers of moles that we have there. So it's literally the fraction of a particular smorgasbord of, if you're looking at gases, if you're looking at a smattering of 3 different gases, it's what fraction of those gases are A. So if I got 10 moles of one, 5 moles of another, you just add all those up and put it over the total number. It's like when you take a percentage of something, except you don't multiply it times 100. It's not anything. I guess I'm saying it's not unique to chemistry. It's you're literally just taking a fraction. Yeah. So those 3 things will be handy. So if you're really not sharp on, especially on molarity, go back and review that stuff. It's in the GChem website in detail. It's not super hard to learn, but if you don't learn it, I don't know how you would get through the rest of the course, especially even the next exam, really. So take some time to go learn that. Okay. But, so now that we have those terms, let's see. We can talk about colligative properties. Sorry, we have to get through my notes here. All right, there we go. So colligative properties, sort of the interesting thing about them that almost makes them not feel super chemical is that, because we don't actually worry about the bonds, is that they do not depend on the nature of the solute. So this is the most important feature of them. What are colligative properties? Colligative properties are things like some of the like vapor pressure lowering, which is really, or at least very closely related to the boiling point elevation. These two things are more or less the same thing. And then also freezing point depression. And the last one that's sort of the oddball is osmosis. Osmosis is kind of the most interesting one, but yeah, I don't know what your familiarity is with this, but like if you're trying to get something really cold, one way to do it is to take ice or take water and dissolve a ton of salt in it, and then throw a bunch of ice in there. So normally water will freeze when it hits 0 degrees Celsius, but if you put salt into the water, you take the freezing point and you depress it, so now it freezes at a lower temperature. So salt water, for example, has a much lower, or can, depending on the concentration of salt, has a much lower freezing point than pure water. And so if you look at like like on the surface of Mars, it's extremely, extremely cold, and pure water has no chance of staying liquid up there. But there are also a lot of salts on the surface, so it's plausible that you might have some extremely briny water that can maintain being a liquid up there. And this is essentially what colligative properties are. It's that when you dissolve things in water or any solvent, we note that their physical properties change, their boiling points change, their freezing points change. And so what we try to look at in this chapter is just like, how do they change? How can we quantitatively say they change? And then we can talk right now briefly about why. So this is sort of an interesting thing up here is like, why does it not depend on the nature of the solute? Why is it that if I dissolve equal number of moles, for example, of sugar, if I take 1 mole of sugar and dissolve it in water, or take what it would be the equivalent of 1 mole of sodium chloride into water, the freezing point, in this case I'm not normalizing for what's called the Van Hoff factor, but don't worry about that now. But if I take 1 mole of 2 different substances dissolved in water, why does that not change the boiling point or the freezing point differently for it? You would expect maybe intuitively that would be different, but it's not. And the reason for that is that if you recall, the delta H, delta H of solution is approximately 0. So, I guess I'll make the caveat that it's not always true, right? Because delta H solution is not always approximately 0. But because delta H is approximately 0, the dominant term is the entropy. So delta S dominates the thermodynamics of dissolution. And so remember that when I back in one of the other lectures, we talked about like what is delta H really when we think about it through a chemistry perspective. Delta H is the change in the energy of a particular system that is related to the chemical bond. So when I form or break bonds, that is the contribution from delta H. So here, because delta H is generally going to be equal to 0, the bond forming or bond breaking, which would be like, sort of in some sense is what you would expect to correlate with the structure of a particular molecule, doesn't matter. It doesn't matter if it's sugar, it doesn't matter if it's sodium chloride. As long as it goes into solution, the delta H is going to be approximately 0. And thus the identity of the bonds being formed or broken just doesn't matter. What actually matters is the change in entropy, and the entropy is kind of ignorant for the most part of what the identity of the molecule is, especially in these really dilute solutions that we're looking at. So the short answer is because the entropy of solution is the entropy is a driving force for solutions in general. It means that the identity of the molecules that you're dissolving just doesn't really matter that much. What does affect the entropy, though, even though it's not the bonds that form or break, is the number of solutes, or the number of moles or particles that do get dissolved. So if entropy is related to disorder, the amount of disorder that you can have in the solution is going to be directly related to, or the number of states, I guess you could say, that the solute can occupy and the solvent can occupy is going to be directly related to how many different particles you actually have in solution. Okay, so the lens that we want to look through is entropy for all of these things. So the entropy is the reason that the boiling point goes up. Entropy is the reason that the freezing point goes down. So before we get into looking at before we get into looking at how these things change, like how the boiling point or the mathematical relationships and such, let's quickly go through what the Van Hoff factor is. So I don't know how this guy got his name on this factor. It's not particularly interesting. Maybe it was like a long time ago when people weren't as smart. I have no idea. But the Van Hoff factor is this factor I, and it's going to look intimidating at first, but once I explain it, hopefully it's not. It's M effective divided by M stated. So it's sort of like the effective number of moles that you have in solution. So for things like ionic compounds, which is probably what we're most familiar with, so 1 mole of sodium chloride, that's a solid, when I put it into water, translates to 2 moles of solute. Because this breaks up entirely, so I've got a sodium chloride, so like when I'm thinking about moles of sodium chloride, I'm thinking of the sodium chloride as a single unit, but when I dissolve it, remember that it actually breaks up into these aqueous bits, and there's 2 parts to it in the solution for every 1 part that you start out with. So I start out with 1 mole of this, but I also have, now I have 1 mole of sodium and 1 mole of chloride in solution. So what's really the amount that I have in there is 2 moles. Yeah, so I think for this, I'm trying to remember how this Van Hoff thing works. So I for this would equal M effective, which is 2, divided by M stated, which in this case is just 1. So I would just be equal to 2. And if you want to put units on it, you could say, well, it's 2 moles and then 1 mole, and then this cancels out. So it's just a pure number of 2. If we look at some other examples of ionic compounds, we can see it changes. If I use calcium, for example, now I start out with 1 mole, which I guess would be M stated. So I add 1 mole of calcium chloride, but what's the actual number of moles that are dissolved in there? Well, it's 1 mole of this and 2 moles of this. So it's really 3 moles. So what's my Van Hoff factor there? It's going to be I is equal to 3 over 1, or it's just equal to 3. What are some instances where we don't have to worry about this? If we look at like sugar, so we looked at glucose earlier. So compounds that are not ionic compounds, essentially. Right, if I take this, I start out with 1 mole, I put it in water. Okay, I guess I can put this here so we can see something happen. Now it's dissolved in water, but I still only have 1 mole of there. It doesn't break up. So the Van Hoff factor there is just equal to 1 because nothing changes. And that's true of any kind of molecular compound. I'm trying to think of other ones, like if you had, I don't know, like an organic compound like, let me look up the structure or the molecular formula for naphthalene so I don't have to draw it out and count. Naphthalene. Yeah, so if you've got something like naphthalene, which is C10H8, and that's a solid. And let's say you can't dissolve this in water, but you could probably dissolve it in like I don't know, like maybe you can get it in acetone. It doesn't matter. But then I dissolve it in acetone, an organic solvent. I don't know how you would signify that. It's not aqueous. Let's just say it's solvated. Yeah, what's our Van Hoff factor there going to be? It's going to be I equals 1. So dissolving organic molecules in organic solvents typically doesn't result in a Van Hoff factor that's greater than 1. One thing to watch out for is that when you have things like, let's say you have sodium phosphate. So typically if you're dealing with organic compounds, your Van Hoff factor is just equal to 1. But ionic compounds are the ones that can be tricky. So if I have something like sodium phosphate, this breaks up into 3 sodiums and 1 phosphate. Don't let whatever's going on over here with the phosphate, the fact that it's got a 4 or something down there, trip you up. This ends up just having this ends up just being 4 moles from 1 moles, and so I ends up equaling 4. So be careful with the polyatomic ions, because remember, these are like covalently bonded internally. Like phosphate is covalently bonded, so it doesn't break up at all, but it's part of an ionic compound. So that can be a little bit confusing sometimes for students. But that's how the Van Hoff factor works. So I think if you take the Van Hoff factor and you understand molarity and molality and that kind of stuff, that's enough to kind of get going on some of these properties, these colligative properties that we go through.